Hi, y'all. So normally I try really hard to get your quizzes back to you before you have another graded assessment. Like I try to get your quizzes graded before you have another quiz. I try to get your quiz graded before you have an exam. But this week is a little different because my dissertation is actually due coming up just in a few days. And so I don't have time to grade everyone's or to get that grade back to them in time, unfortunately. But I did want you to be able to look over the quiz material and kind of have a better understanding of what's going on. Uh, or like you can answer any questions that you weren't sure about when you were taking the quiz. And I know that's not ideal, but unfortunately, that's the best I can do this week. But I promise that I'll have both of these quizzes graded for you before your exam. So let's go ahead and get started on quiz 5. So quiz 5 is a virtual quiz. So I'm just going to draw out the questions. So the first one was rank the following compounds in decreasing order of reactivity. So basically, which is the most reactive, which is the least reactive. So these were the molecules. And this is actually pretty similar to the group work that we did just on Tuesday of this week. So the chapter 17 group work, this is all about which one of these is the most reactive. And reactivity is all about like, well, we have this partial positive center here, and which one of those is going to be the most easy to attack. The most easy to attack is going to be ones that have either electron withdrawing groups or they're not stabilized by any electron donating groups. So as you hopefully remember from our aromatic rings, which is kind of the context we learned this in, if you just have hydrogen, that's like kind of a neutral, right? You just have neutral hydrogens. And then if you have a methyl group, that's electron donating. And if you have even more branched methyl group, that's even more electron donating, and it has some steric hindrance. So in this case, if we have our carbonyl carbon, it does have a resonance structure, right? That has a partial positive down here on the bottom and the negative here. So this resonance structure is going to be more stable if it has two methyl groups than if it has two hydrogens. And that might be hard to see just like when it's drawn out the way it is there, but it's easier to see when it's drawn like this because when have you ever seen a primary carbon have a carbocation, right? Like that doesn't happen. It's not very happy. So this is going to be a lot more positive, right? It's going to be less stable. It's like it doesn't want to exist in that form. So as fast as it can get out of it, it's going to. So, and that's because there's very little electron density coming from those hydrogens to help stabilize that positive charge. So the faster it can get out of that situation with a positive charge next to just some measly hydrogens, it will. So this is the most reactive. And then you kind of just go up from there. So if we substitute one hydrogen out for a methyl group, that's next most. This with two methyl groups, that's next. So let's put this at 1 and then 2, 3, and then you're going to increase from there. So more carbon is more electron density to donate. So if we swap out one methyl group for a more branched carbon, it also has steric hindrance, so that makes it even less likely to react. And then the very least likely to react is this one that has 2. So this is the most reactive, and then this, and then this, and this, and this is the very least reactive. So that question on your quiz was just asking you to rank the I think it asked most to least reactive. So this would be number 1. That should be the first one, and then actually 5 will be the last one. Okay, and so the next question was explain your reasoning to 1. My reasoning for that is just that the partial positive on the carbonyl carbon is less stabilized by hydrogens that don't have electron density to donate, and it's more stabilized by carbons, even more so by branched carbons than just one carbon, like the extra carbons are better, and once you have branched carbons, there is some steric hindrance, so that makes it even less likely to react. So some variation on you showing me that you understand that is what we'll be grading for. The next question is, what reagents will carry out the conversion shown? And that's just going from NH2 to N double bonded to 1, 2. I might have one too many carbons on there, but you get the idea. And when I see an amine go to a nitrogen double bonded with a carbon, I know that this is an amine formation, or enamine. Also can come if the nitrogen has a bond one away. And so you need a carbonyl carbon of some kind, and whatever R groups were present on the carbonyl carbon are going to be maintained on this amine. So in this case, I may have added a carbon. I think I did, but it'll be something along these lines, whatever your R group is here. And that's all that happens is basically your oxygen just swaps out for your nitrogen. But whenever I have a question like this, I don't know why I drew two lone pairs. Whenever I have a question like this, I always work it forward, actually. So like this nitrogen comes, attacks, kicks up, and you get your, I do this just to make sure that I know what's happening. And I catch any mistakes that I make. And actually on the group work that I just posted, I was like, oh, this will have a methyl. And if it had done that, I would have got the question wrong. But I caught myself when I worked it forward. So this would be the first step. And then this would get deprotonated. And you'd get an H with a single bond to this OH here. And then that would get protonated by something else and become OH2 plus, and the lone pair will come here and kick this out, and then you would get nitrogen. 1, 2, 3. Yeah. So basically you just need your ketone there, or your aldehyde there. And so then that's the next thing you need to be able to name this structure. So you need to know this structure, but you also need to know which one of these multiple choice is the right name. And this is where me not having the right number of carbons comes in, because I think I did, for mine, what I did was 4 carbons, so that's butane. So the aldehyde version of that is actually butanal, Al for aldehyde. If you have a ketone, it's butanone, one for ketone. So ketone has O-N-E, aldehydes have Al, so those are actually pretty easy to remember, I think, in terms of like nomenclature. So we're looking for the propanal, and then you also need the acid to protonate this oxygen. Excuse me for the leaving group. So I would say that would be probably, this is only 3 carbons get added. So instead of butanal, you need propanal. And the only one that has propanal is B. So, but yeah, that's just an amine question. Draw the mechanism of the previous reaction. I did that for you. And then provide the structure of the reagents necessary to prepare the following. So whenever I see a carbon-carbon double bond get formed, I know that's a Wittig reagent. So before I pick my answer or even look at my multiple choice, I'm focusing right here on this carbon-carbon double bond. So one of the, that looks bad, but on one side you have this, and on the other side you have this. So you can actually have either your oxygen or your PPH3, either one of these will work on either one of these. So if you mix this plus PH3 double bonded to this, it's a 5-membered ring, that will work. Or if you have it swapped, so if you have this PPH3 plus, either of those will work, as long as these are around the double bond. So I'm looking, and it looks like the only one that has a combination of these two is answer choice C. And really the way that I do these is I'll just go ahead and line up. Here, let me just draw starting from here. I'll just line up the PPH3 with the O. It looks like this. And then I do the box. And so then you have a box made up of your carbons, one with your phenyl chain, hydrogen, and this one has its 5-membered ring. And then the reaction actually, and this still has PPH3 on it, and then this reaction will actually happen again, where this will come here, and this will come here. Now you have your double bond, and you have your hydrogen and your phenyl, and then you're just like that. So that's kind of how I work this reaction. Okay, next question. What is appropriate stepwise reaction for this synthesis shown? So you can do this when you have a multiple choice like this. You can kind of approach it one of two ways. You can either try to come up with your own transformation. That's kind of useful because you might have a question where you have to come up with a transformation like this on the examine the free response portion. But you can also just do a process of elimination and see which one of these that you think would work. I scanned the answer choices quickly and saw that there's a Grignard reagent involved. So I'm kind of going to do actually a mixture of that. And I'm going to say if I use a Grignard reagent here, what would I need to react it with to get this? And then when I had that thought, then I was like, wait, well, Grignard reactions actually usually make alcohol, so I think there might also be an oxidizing step. So then I checked the answer, and it looks like these answers do have all oxidizing steps in them. So I'm going to use that little bit of information I have. I know that it's a Grignard. I know that there's an oxidizing step, so I don't have to come up with completely my own synthesis. But I also can kind of check myself and exercise my brain power, to just kind of see what I think you would need. And so the first thing I see is if this is our Grignard reagent, the carbon bond forms from here to here. So I need all of this present in the thing that it's going to attack. It only has that carbon right there, so it's not a ketone, it's an aldehyde. And then the Grignard will attack and come here, and we'd get O minus. So if this had been a ketone instead of an aldehyde, we'd have an R group right here that was present right there. But because there's not, this is just a hydrogen. And then if I added H plus, I would get to an alcohol. And then I can use any oxidizing agent, PCC, Jones reagent, or KMNO4 to, actually KMNO4 in this case might cleave this and turn it into carboxylic acid. So I'd only use PCC or Jones reagent and go from here to here. And the only one that has that process is A. Okay, I hope that was helpful for you. If you have any questions for me, just let me know, and good luck studying for your quiz.